Hi Year 10, this is our second lesson for our probability topic multi-step experiments. In this lesson we're going to look at compound events. So last lesson we did a review of probability. We looked at sample space, complementary events, theoretical probability and experimental probability, which is also called relative frequency. Now this lesson we're going to look at the difference between simple and compound events, Venn diagrams, two-way tables, the language of probability, mutually exclusive events, and we'll finish off with the laws of probability. Now a simple event involves only a single experiment, like tossing a coin. But a compound event involves a combination of two or more events. These events can happen in a sequence, which is a multi-step experiment, or they can relate to two or more subsets of a single experiment. Now there are a number of ways to organise the sample space, but we're going to specifically look at grids, Venn diagrams and two-way tables. Okay, we'll start off with using a grid. Two six-sided dice are thrown and the totals recorded. What is the probability that the total is greater than or equal to 7? So here's the grid, and we can see that we've got one die here, and the numbers 1, 2, 3, 4, 5, 6, and here's the second die. And inside here are all the totals. So suppose we've got a 2 and a 1, the total is 3. So we want the total being greater than or equal to 7. So that's everything 7 and above. So all of these and all the way up to 12. All we need to do is count all of those. There are 21. And the total number of outcomes is 6 times 6, which is 36. So our probability is 21 over 36. Let's move on to Venn diagrams. In a homeroom class of 25 students, 15 study chemistry and 18 study biology. 2 students study neither chemistry nor biology. Draw a Venn diagram for this scenario. Now, if this is the first time you've seen Venn diagrams, you're probably a little confused. You might be saying 15 study chemistry and 18 study biology. That's more than the students we actually have. And you're right, because we've double counted. Some students study chemistry and biology. Let's start by drawing up the Venn diagram. We have overlapping circles and we have C for chemistry and B for biology. We need to find this overlap. So we're going to add the chemistry students and the biology students and the 2 students that study neither chemistry nor biology. And so we have got 35 students, so our overlap must be 10. And 10 is what goes in here. Now we have 2 students that study neither chemistry nor biology, so they go outside. And then the trick is to fill in the circles. Now these are all the chemistry students, so that is 15. We've already counted 10 of them. What goes in here? These are the people that study only chemistry. That must be 5. What about in here? We've got 18 altogether. 10 have already been counted. This must be 8. A quick check is to add these numbers. 5 and 10 is 15, and 8 is 23, and 2 is 25. So we're correct. Once we've drawn our Venn diagram, we can use it to answer questions. One student is chosen at random. What is the probability that they study both chemistry and biology? So we want that overlap. So there are 10 students who study both chemistry and biology out of 25. What's the probability they study only chemistry? And so that's going to be just in this part of the circle. So 5 out of 25. And lastly, what is the probability they study chemistry or biology? And when we use the word or, we mean chemistry or biology or both. So we want 5 plus 10, which is 15, plus 8, which is 23. And we need to write it as a fraction, so 23 out of 25. Now let's look at two-way tables. They're just another way of organising information from an experimental situation. Some people prefer two-way tables, some people prefer Venn diagrams. Here's the same question. 25 students, 15 study chemistry, 18 study bio, 2 students study neither chemistry nor biology. And here's our two-way table. Have a look how it's different. We've got one of our attributes here, biology and not biology. We have the other attribute here, chemistry and not chemistry. A Venn diagram doesn't have these not parts. And then we have totals here and totals along here. So having a look at our question, we have got a total of 25 students, so let's put those in just here. We know that 2 students study neither chemistry nor biology, so they go in there. We have 15 students who study chemistry, so here's chemistry, and there's the total of chemistry students, which is here. And we have 18 students who study biology, here's biology. Let's put in a total there of 18. And from this, we can work out all of the others. So 15 and something must make 25, so that's 10. Along the bottom here, we've got 18 and something makes 25, that's 7. Coming up here, we've got something or other, and 2 makes 7, that must be 5. Now let's go along this way, along this top row. 15 take 5 must be 10. And then finally, coming down here, 10 plus 8 is 18. And we can check that last row adds up. And that's how we fill in a two-way table. Now the language of probability is really important. And we use these words when we're talking about compound events. If we say the word and, we mean times. If we say or, we mean plus. If we say not, we've got to find the complement. At least and at most are also important words. Now I mentioned this before, we worked out the probability of chemistry or biology, and I said it's chemistry or biology or both. And there are actually 2 types of or in probability. There's an inclusive or, which means A or B or both. That's the one we did. There's also an exclusive or, and so that means A or B, but not both. Can be a little confusing. Here's the general rule. If the question doesn't say it explicitly, it's an inclusive or. It means A or B or both. Here's an example. Henry tosses a coin and a 6-sided die. Let's write the sample space. So we're going to have heads and tails, and we're also going to have 1, 2, 3, 4, 5, 6. So we can get a head and a 1, a head and a 2, head and a 3, head and a 4, 5, 6. Can you see all of those? And then we can get the same with the tails. Tails 1, tails 2, 3, 4, 5, 6. So there's 12 outcomes altogether. Find the probability that he throws a head and a 6. Well, how many ways can that happen? 1 out of 12. What's the probability of a head or a 6? So that means heads or a 6 or both. So all of these guys, because they've got heads, and this one, and we will include that. So that's 7 out of 12. Head or a 6, but not both. So 1, 2, 3, 4, 5, not this guy, but include this one. So 6 out of 12. Or a half. Now 2 events are said to be mutually exclusive if they don't contain any common elements. And it means in our Venn diagram, the sets are not going to overlap. Remember before we had overlapping circles with the biology-chemistry experiment because we had some students take both biology and chemistry. Now let's have a look at this experiment where we had the coin and the die. Let this set be the outcomes of the coin, so that could be heads or tails. And this set be the outcome of the die. That's the numbers 1, 2, 3, 4, 5, 6. There's no common elements. So therefore, they are mutually exclusive events. When 2 events contain some elements that are common, they are said to be non-mutually exclusive or not mutually exclusive. And this is actually a phrase we use in English. Here's an example. Making money and doing good in the world are not mutually exclusive. So what do you think that means? It means that you can make money and do good in the world. Hopefully that makes sense to you. Let's look at an example. A card is drawn from a standard deck. Are the following events mutually exclusive? So we've got 2 sets. We've got the set A, which contains all of the aces, and the set H, which contains all of the hearts. Are there any common elements? There are, aren't there? There's just the one, but the ace of hearts appears in both sets. So the events are not mutually exclusive. In fact, if we drew them as a Venn diagram, this is what we'd have. Here's our aces here. Here's our hearts. There's our common element there, the ace of hearts. Now we're going to look at a bit of formal set notation, which is going to be important for years 11 and 12. This is the same question that we used before, and we've drawn the Venn diagram. Now remember, I asked you some questions about this. One student is chosen at random. Now I'm going to ask, find the probability of C intersection B. So this is the same as C and B, chemistry and biology. So this is called the intersection of the two sets. It's where they overlap. So the probability that they study chemistry and they study biology is still going to be the same answer, 10 out of 25. Okay, so that's the intersection of the two sets. Find the probability of C union B. Now this is the same as or, chemistry or biology. And this is called the union. So everything in C and everything in B and everything that overlaps. So same answer, 5 plus 10 plus 8 over 25, which is 23 out of 25. And finally, find the probability of C with an apostrophe next to it. Now this is the complement of the set. Now, before I told you that the complementary event was C with a line over the top, well, that's probability notation, and this is set notation. They mean the same thing. So this means not C. If we look at it diagrammatically, we want everything that's outside of that circle. So we want 8 and 2. So our answer is going to be 8 plus 2 out of 25, which is 10 over 25. Okay, the last thing we've got to learn for this lesson is the laws of probability. And there are two. There's one for intersection and one for union. The probability of A intersection B is just equal to the probability of A multiplied by the probability of B. We might sometimes write it like this without the times sign, but you should be used to that from algebra. Then there's this one. The probability of A union B is equal to the probability of A plus the probability of B take away the probability of A intersection B. Now here's the thing. If the events are mutually exclusive, then this part here is going to be equal to 0 because there's no overlap. So we will just write it like this. But on your formula sheet, you're only going to be given this formula and this one. So you'll have to work this part out yourself. Let's see how we use it. Consider the two events. A is that we draw a counter from a box containing 4 blue and 3 green counters. B, we draw a counter from a box containing 7 blue and 2 green counters. James draws a counter from each box and notes the colours. Find the probability they are both green. So we want probability of green from the first box, and means times probability we draw a green from the second box. All right, what's the probability we're going to get a green from this first box? 3 out of 7, and, which is times, green from the second one is 2 out of 9. And all we have to do that is do that on our calculator, and we get 2 out of 21. The probability of different colours. Okay, so that could be that we get a blue here and a green, or, which means plus, a green, then a blue. So we've actually got both rules happening here. Blue and green, or green and blue. So probability of blue in the first case is 4 out of 7. Times, because we're saying and, green in the second box, which is 2 out of 9, or, which is plus, green in the first, which is 3 out of 7, times blue in the second case, which is 7 out of 9. Okay, just have a look at that for a second and make sure that makes sense to you. And on our calculator, and we get 29 out of 63. Now let's look at a non-mutually exclusive example. A card is drawn from a standard deck of 52 cards. Consider the events. A, an ace is drawn, and H, a heart is drawn. It's the same example we looked at before. They're not mutually exclusive events because they have the ace of hearts in common. We want to find the probability of A union H. Here's our formula. Probability of A union H is equal to the probability of A plus the probability of H take away the probability of A intersection H. Okay, probability that we draw an ace is 4 out of 52. Probability we draw a heart is 13 out of 52. Take away, the probability that it is the ace of hearts is 1 on 52. And doing that on the calculator or in your head, we get 16 on 52. Now in that previous example, we could have done it just by looking at the cards and adding them up. But sometimes there's no context given and we actually have to use the rule because we don't know what the experiment is. So like this, the probability of A or B is 0.8. Probability of A is 0.2, probability of B is 0.7. Are the events mutually exclusive? So here's our rule. We want to substitute these all in and see whether this intersection, the overlap between the sets, is equal to 0 or not. If it's equal to 0, they are mutually exclusive. If it's not equal to 0, they're non-mutually exclusive. Let's substitute the numbers in. Here we've got 0.9, so 0.8 is equal to 0.9, take away 0.1. This is not equal to 0. Therefore, the events are not mutually exclusive. Okay, that's it for the lesson. There was a lot in that, so you might need to go back over it. Our next lesson is on tree diagrams.